Alright, so this is chapter 3. We get into derivatives, or at least shortcuts of derivatives and different rules. So 3.1, derivatives of polynomial and exponential functions. There are the learning objectives. So we want to basically be able to use the power rule. That's the big lesson of the section. And a couple of these other things we'll hit as well. Okay, so first let's kind of find this d dx is notation saying that we're going to find the derivative. So we're going to find the derivative of c. So let's say that c is a constant, so it's just a number. That always equals 0. So without exception, the derivative of a constant is 0. Why is that? Now remember that when we were doing this before, we said that the derivative is the slope of the tangent line of a function. It's the same thing. It's the rate of change of the function. So if it's 5, then that means it's like a straight line here, and the function isn't changing at all. And so it makes sense that the derivative, being a rate of change, says, hey, the function's not changing, so it's actually just 0. Okay? So the graph of this, the graph of the derivative, would be just a straight line right here on the x-axis. Okay? Alright. Another kind of special type before we get into the power rule is that the derivative of x, just of this particular function only, the derivative is 1. So that makes sense too, that if you think about this function, y equals x, the slope is always 1, and so that means, it's a constant function, or constant rate of change here of 1. So you just remember that every time you find the derivative of x, that's equal to 1. Alright, and then this is just if you care about, kind of proving the definition here, that it makes sense that the derivative of x is actually equal to 1 using the actual definition of a limit, one of the two that we learned, but not a big deal. Alright, here's the big rule of the section. It's called the power rule, and we'll use this for the rest of the year. When you find the derivative of a function like this, whenever it's a polynomial function, whenever it's x raised to a power, basically, then every time you find the derivative, you're going to take whatever this power is, and you're going to bring it to the front, and then you're going to rewrite the x, and then you're going to reduce this power by 1. So whatever that power is, you just reduce it by 1. Okay, so let's look at an example 1. d dx of x to the 7th, what you'll do is you'll bring the 7 out in front, you rewrite the x, and then reduce it by a power. So that would be x to the 6th. Okay, so final answer, that's your derivative. Extremely shorter than what we were doing in chapter 2. Example 2, if y equals x to the 100th power, then y prime, which again is a way of saying I'm going to find the derivative. So y prime is just another notation for saying I'm finding the derivative. So y prime would be, I would take the 100, and I'd bring it out in front, and then I'd rewrite the x, and then I'd reduce that by a power. So that would make it x to the 99th. Okay? So it's circled out. Okay. Then example 3, if y equals t to the 5th, then I could find the derivative, and one of the forms of notation for derivative is I could say I'm finding the derivative of y with respect to t. And so again, I can use the same power rule, so I would bring the 5 out in front, I would say t, and then I would reduce it by a power. So I'd say 5t to the 4th. That would be my answer. Okay? Whenever you have a function that has a constant in front of it, like just multiplied by it, then the way that you calculate the derivative is you just bring the constant along for the ride, and then you find the derivative of the function. So if I'm finding the derivative of 4x to the 5th, then I just keep this 4 along for the ride, and I do the power rule on the x to the 5th part. So I bring the 5 out in front, you can see that, and then I reduce this by 1. So you can see the x to the 4th, and then I would simplify it, and I would say 20x to the fifth. Now I just want to look at this graphically to see if it makes sense that we should carry this little constant along for the ride, and just kind of check it out, see if it seems reasonable. If you start off with y equals x squared, we know it's just a parabola like this. Y prime would be bringing the 2 out in front and then reducing this by a power, so that would be 2x to the first, or just 2x. And then this one over here, you bring the 2 along for the ride, so it would be, if you were finding the derivative, then it would be y prime equals 2, then of course you'd bring that 2 out in front, and then it would be x to the first, or 4x like I have here. Does it seem like the slopes are twice as steep? Because whatever number you plug in to these, it's going to be twice as steep here, and so again that corresponds to the slopes of the tangent lines. Seem like it's twice as steep? Maybe seems reasonable. So it is a true statement. And yeah, so that's what the 2 in front does. It makes your parabola a little skinnier, so it vertically stretches it. Alright. Now remember all those boring laws that we did? I think we did about, I want to say about 9 boring limit laws. Well, all of those limit laws apply to derivatives. So, add them equals the same thing, you subtract them equals the same thing. So here are just a couple. This one, the derivative of a sum equals the sum of each of the separate derivatives. So I think you might remember that with limits. And then remember we said the limit of a difference is the same as the difference of the limits. Well, same thing with derivatives. Alright, check. Alright. Now, the reason why the limit laws were important is because, remember, we could find the limit of a polynomial by just combining all of those laws. And we said we really wouldn't do them separately, we'd actually just kind of put them all together. So that's what I want to do here. So first things first, you got to make sure that if you're going to find the derivative of a function, you have to make sure, if you're going to use the power rule, you got to make sure it's set up right. So it needs to be x raised to some power. So not all of these are really set up right. So I'm going to rewrite this function. So this one's okay. This is x to the 8th, so I'll just rewrite it. And this one's okay. You can go with that. This one's not okay, so I'm going to have to say that this would be x to the... Now this is x to the 1/2, but the fact that it's on the bottom and I want to put it to the top, then I have to make it x to the negative 1/2. Make sure you're comfortable with radicals and changing them to fractional exponents. That's going to be important. And then this is actually x to the 1/2, so this is x times x to the 1/2. So it's really x to the, and you'd have to keep the base and you'd add the exponents. So this would actually be x to the 3/2. So that's algebra. This is 2/2. When you multiply those, you keep the base, you add the exponents. Then we have plus 5. Alright, so it's all ready to roll as far as the power rule goes. Now we can go ahead and find the derivative. So we're going to go f prime of x equals, we're going to bring the 8 out in front, we're going to reduce this by 1, so 8x to the 7th. We're going to carry the 3/4 along for the ride. We're going to bring the 4 down in front. We're going to reduce that by power, minus, because that minus. Then we're going to bring this minus sign out in front, so that would be minus 1/2, and then x, and then we're going to reduce that by 1. So when you reduce that by 1, that's minus 1, or minus 2/2. So that means, what's negative 1/2 minus 1, which is actually minus 2/2, which equals negative 3/2. So this becomes x to the negative 3/2, and then plus, and then we carry the 10 along for the ride, and we multiply the 3 as well. So I'll go ahead and just multiply those two together. Well, never mind, I'll carry the 10, bring the 3 out in front, and then reduce it by 1, plus, now I'm going to bring the 3/2 out in front, x, and then I have to reduce that by 1. So if I reduce it by 1, that's minus 2 halves, so that makes it x to the 1/2, plus derivative of all constants, 0, so I lose that part. And then now it just becomes, how simplified do we want to make this? So obviously, this is just a cleanup job. So this would be 3x cubed, and then negative negatives, that would be plus 1/2 x to the negative 3/2, and then we got plus 30 x squared plus 3/2 x to the 1/2, or if you wanted to make it a square root of x, either way. So x to the 1/2, I'll leave it, and that would be good. That would be the derivative. Okay. All right. Let's see here. Let's see if hopefully I have the same thing here. Let's see. 30x squared, 3/2. Okay, I think that looks good. Okay. All right. Now, this is a rule when you want to find the derivative of an exponential function. Now, an exponential function is a function that has the variable as the exponent. The rule for that is that you rewrite it exactly the way that it is, and then you multiply by the natural log of whatever the base is. That's something you just memorize. That's how you calculate the derivative. So if the first one, you want to find the derivative of 2 to the x, that particular function, then you write the exact same thing, 2 to the x, and then you write natural log of whatever the base is. So this is the derivative. And again, that describes the slopes of the tangent lines at all of the x values for this particular function. 3 raised to the x, derivative of that would be the exact same thing, and then you got to multiply it by natural log of the base. Derivative of e to the x is e to the x, and then natural log of the base. The natural log of the base, so that would be natural log of e. But natural log of e is actually equal to 1. So your answer is still e raised to the x. So this is an interesting function because it's the only function that when you find the derivative of it, you get the exact same thing. So the slopes of the tangent lines are equal to the same thing. It's a very unique function. So you could take the derivative all day long for this. First derivative, second derivative, third derivative, keep taking the derivative, you get the exact same function. Okay? This is something that's on the AP test. E is described as a number such that it's just this interesting property. Okay, so limit as h approaches 0 of e raised to the h minus 1 over h equals 1. So again, kind of just something you memorize, not too big a deal. All right, I think this will be my last example. We want to find all the points on the curve, this particular curve, where the tangent line is horizontal. Now, if the tangent line is horizontal, what would the slopes be? What would you say the slopes would be? Pause for a second. Oh, no one's answering. Oh, well. So what we would do is we would say, let's figure out the derivative first, because that's the slopes of all the tangent lines. So let's find the derivatives. That would be 4x cubed minus 12x. Okay, so what I did, you can tell what I did. I put the 4 out in front, reduced that by a power, brought the 2 out in front, reduced that by a power. Now, this describes the slopes of the tangent lines. Now, where are they horizontal? Well, that would be whenever they're equal to 0. So then we'd set it equal to 0, and we want to try to figure out all those x values where the tangent line is horizontal. So we would factor it. So we take out a 4x, then that would be x squared minus 3. And then we'd set each of those factors equal to 0. Let me see if I work this out. Okay, so I did. So you factor it out, like I did there, and then you set each of the parts equal to 0 to find the answers. So this part set equal to 0, I get x equals 0. That's one of the answers, or that's at least the x coordinate. And then this one, we set that equal to 0, and we get x squared equals 3. And then solving for x, we would get plus and minus radical 3. Now, if they asked where that occurs, it says where, it says find all the points. Now, a point is an x and a y coordinate, right? So on a graph, a point is an x and y coordinate. That's a different question than saying where on the curve is the tangent line horizontal. If they just say where is it horizontal, a lot of times that's just the x coordinate. But it's better to give both coordinates if you can, because that really gives the location. So these are the x coordinates, and then we could, if you ever want to find the y coordinates, you just always want to plug them into the original function. So we take each of those, we plug them into the original function, which again, that original function is, x to the fourth, that one, that's the one. So that's why this is raised to the fourth, and then it was minus 6x squared, and then plus 4. So you take each of those x coordinates that we found, and you plug them in. So we get -5, and so radical. When you plug in radical 3, you get. Let's see, what did we say? Oh, -5. So when you plug in radical 3, you get -5. So that's right here. So this is radical 3, -5. And then what you can do is you can use symmetry. If you recognize that this was an even function, then this would be the point negative radical 3, comma, -5, that point there. And then this point, when you plug in a 0 into the function, you get 4. Okay, so notice this particular function, that's where all the tangent lines are horizontal, so it makes sense. Okay, so I think that will probably do it for us. Hopefully that makes sense to you, and you'll be able to work on the 3.1 in class both days.